Good afternoon. I'll give it a minute, so let the participants join, and then we'll make a start. How are we doing? Okay, so let's make a start, given that we have a finite time. So I just want to welcome everybody to our August Tech Talk. I'm absolutely delighted to have Bonyadi from Lyra Electronics join us today. And before I introduce Yagi, I just want to maybe give you a quick background of ASIN for those who don't know who ASIN is. And then we can move to the talk. So ASIN is the Automotive Electronic Systems Innovation Network, established 12 years ago to bolster UK's position as an innovation lead for electronics. We've been operating now for 12 years. We've had our 10th conference anniversary last year. We've just finished our 11th conference this year in July, and we hosted that at the British Motor Museum in Gaydon, which was a resounding success. So we're absolutely delighted that we can be working with some of the smartest minds in the UK when it comes to automotive electronics. The way we're structured, we have a number of interest groups around which our members converge to talk about important topics. And right now, one of the most interesting groups we're starting off, pertinent to you all on the call today, is around power electronics and control systems. And that we're keen because there's a lot of interest around the development of power electronics as a community, as a capability in the UK. And we want to see what we can do to develop that through our network. With that, it's a nice little link in now to our talk. So Yegi joins us from Lyra Electronics, as I've said. And Yegi is an electronics team lead at Lyra and has a PhD from the University of Warwick, which is very dear to my heart because I spent over 15 years at Warwick University and became good friends with Professor Phil Morby, who I believe was Yegi's supervisor, who's an absolute genius in this area. So Yegi's work is around the design of high-power DC to DC converters, onboard chargers, and cost-effective design, EMC design. And that is where a lot of our interest lies, and especially around wide bandgap semiconductor devices. So I'm going to hand over to Yegi in a second. What I'll ask you to do is if there are questions, please pop them in the chat. And at the end of the talk, then I'll pick up a few of the pertinent questions and we'll then pose them to Yegi to answer. So with that, Yegi, the stage is all yours, and thank you very much for taking the show today.
Thank you very much, Connie. So hello everyone. I'll just start sharing my screen. Yeah. I hope you can see. I hope you can see that now. So yeah, I'm Yegi. I'm from Lyra Electronics, and today I'll just give you a talk about EMC design techniques for high power DC-DC converters, mainly the ones with silicon carbide MOSFETs in them. Just before starting, I'll give you a little bit of background about myself and Lyra Electronics, and then I'll present to you the case study that I want to talk about today. So as Gani mentioned, I'm the principal engineer and electronics team lead at Lyra. We focus on power design for power electronics for automotive application and marines, medical, and any other application that needs power electronics. But my main interest is DC-DC converters, onboard chargers, and effective cost-effective EMC design. At Lyra, we do everything from simulation, prototype design, test and validation, and we've got teams including electronics, mechanical, software, system, test, and validation. And we have recently got our own EMC and environmental test facility, where you can see the picture of in this slide. So we do have our own capability to test conducted and radiated emissions at Lyra. This is a CISPR 25 semi-anechoic chamber. The dimension, it's around 6 by 6 meter wide, and also we can also do environmental testing, where we've got dynamic climate chamber, and we've got a humidity control as well. So in this test facility, we can test and validate for power electronics for automotive, off-highway, marine, aerospace, and not only for Lyra, but also we do offer this as a service for external customers as well. So if you have any interest in this, please get in touch. So now I'll just get on with the topic of this talk, which is the automotive DC-DC converter. So I'll talk about how a CISPR 25 testing method is, what conducted emission test setup should look like, and I'll show you some of Lyra's test setup and how we troubleshooted our EMC issues, how we find sources of EMI, and what techniques to use to improve the results. And at the end, I'll show you how the emissions were improved and how we passed our EMC test. So this is showing you a little schematic of a dual active bridge DC-DC converter. In electric vehicles, they use two different power systems: a high voltage battery, which you can see on this side, and in this case, it can either be 800 volts or 400 volts, and also a low voltage battery, where supplies all the electric appliances in the car. In this case, we've got a 24 volt or 12 volt version of this. So on the low voltage side, we can have something between 150 amps to 300 amps. So it's quite high current. And the DC-DC converter that I'm going to talk about is 4 kilowatt rated and uses silicon carbide MOSFETs in the high voltage side here. So as you know about silicon carbide, they do have large dV by dt and di by dt events, which causes high electric and magnetic field, which are both sources of EMI. And if you're relying on having Y capacitance just to solve your EMC issues, I think it's time to review your design, because every time you double your voltage, the available Y capacitance is reduced by 75%. So it's important to think about EMC and not just rely on Y capacitance. For this converter, we had to comply with CISPR 25 automotive EMC standard, which I will talk to you about it in the coming slides. So as I mentioned, EMI is quite important. It can no longer be an afterthought. So it's got a potential to cause significant setbacks later in the design that can cost both time and money. So always think about EMC from the beginning, from PCB design stage, where you're selecting your components, have EMI in mind. If you're placing components in the PCB, you have to have EMI in mind. Identify your di by dt and dv by dt circuits and nodes, and minimize the surface areas for these components. And also need to be really careful about your PCB layout. If you've got cables, bear in mind that cables can radiate, and conductor path through cabling is quite important. And also knowing how to design filters to be effective in the frequency range that you're interested in is quite important. As I mentioned, CISPR 25 is what we had to test to, and you can see on the diagram down below, the conducted and radiated emission tests have different frequencies that you need to test them in. So for conducted emission tests, the range is from 150 kilohertz all the way to 108 megahertz, and radiated emission test goes from 30 meg all the way to gigahertz. So CISPR 25 testing method provides you with defines two methods. One is using a current probe, and the other one voltage method. So both of them can be used. It depends on your OEM requirements. If they want to use the current method or voltage method, they will need to let you know. But in the table that I'm showing here, it shows you the CISPR 25 passing limit at different frequencies for voltage method in the middle column, and also the current probe method on the right-hand side column. The limits given for voltage method are from CISPR 25 standard, whereas the limits for the current probe method are converted from CISPR 25 standard units. So they're converted from dB microamp to dB microvolt for comparison. So you can see what the comparison between using these methods are. So here I'm showing you the EMC test setup for conducted emissions based on CISPR 25. On the left-hand side of the slide, there are two pictures. They show you how you need to set up your test, how the device on the test should be placed. You can see the big ground plane here, and how the device has to be placed on a low relative permittivity support, which is around 5 centimeters. And then it has to be bonded to the ground plane, the same as your LISNs and the power supplies. The length of the cables are quite important, so always refer to the standard for these. And before, because we didn't have our, we've just got our EMC test facility, but before getting those, we had set up this little conducted emission test setup at Lyra, where we did some of our tests for this project. This was around a year ago. You can see the ground plane, the device on the test, the LISNs. This one is the high voltage LISN and the low voltage one as well. And the length of the cables and how they should be placed is also based on the standard. The CISPR 25 standard also shows you the test setup that you need for radiated emissions. So again, it shows you how you need to place the antenna, what position the antenna should be, what's the distance between the cables to the antenna, and how the cables should run from the device all the way to your measurement. So these are quite important to have that in mind. And if you're setting your test in your lab, just make sure that you do set them up according to these test standards. Okay, so spectrum analyzers are normally used to measure the emissions, but they cannot distinguish between common mode noise and differential mode noise. In this slide, I'm showing you the difference if you use a discrimination network between your LISN and the spectrum analyzer. You can separate common mode from differential mode noise. So in the graph on the right-hand side, you can see how this is shown. It does help a lot when you're trying to troubleshoot your device. If you're failing, for example, in this case, if you're failing between, let's say, 80 to 100 megahertz, and you can just separate them to know if it's more common mode noise or differential mode noise, and then design your filters according to that. As I mentioned, you can also use current probe for doing your troubleshooting and testing. Both current probe and using a LISN, they show very similar results in low frequency, but in higher frequency above 5 megahertz, there can be some differences. And there are a few possible explanations to explain why these differences are. The first one would be that the current probe position is quite important. In CISPR 25 standard, they specify two locations where you should place your current probe. One is 50 millimeter away from the unit, and the other one is 750 millimeters away. So by placing the current probe at different distances from the device, certain harmonics become more apparent at specific locations. So that can be an explanation why you would see different results compared to LISN. And also the diameter of the aperture of the current probe is quite important. If you use smaller aperture, the more it will be more efficient. The coupling will be more efficient. If you have a current probe with a larger aperture, they're optimized either for low or high frequency coupling efficiency. So this can be just the explanation as to why you see some differences. As you can see here on this graph on the right-hand side, LISN measurement and current flow measurement, you know, the trend is the same, similar, but you've got a bit of differences in high frequency range. And this is also, again, showing the same thing, but I'm showing you from 150 kilohertz, the spectrum, and this is the conducted emission test result from 150 kilohertz all the way to 100 meg. And you can see below 20, 30 meg, it is almost the same, similar, but above that, there are some differences between using these two methods. Okay, so now these are the results of the first emission, the conducted emission results that we got from testing our DC-DC converter. Just to let you know that we have to test according to CISPR 25. You have to test every cable coming out of your device. In our case, there is one high voltage cable, which was the 400 and 800 volt cable, one low voltage high current, which is the 12 or 24 volts with 300 amps or 150 amps, and another one is the the comms cable, which is low voltage and low current. In this slide, I'm showing you the low voltage high current LISN on the left hand side, and then the emissions from the high voltage LISN on the right hand side. And you can see that it's basically failing everywhere. It was quite bad initially how it started. And then later on, I'm going to show you how we tackle this and troubleshoot it and fix the issue. In this area that I've highlighted, it mainly shows you the switching frequency, which in this case was 50 kilohertz, and the harmonics of the switching frequency. You can see they are actually the main contents of the why we're failing. So that was quite important. And then looking at this slide, this is the same cables, but from 30 to 108 megahertz for both high voltage and low voltage. And again, you can see that we were failing again in this region. And something that was quite important was that to know that if in this case, if you have conducted emissions and you've got big peaks, these cables will actually act as antennas, so they will radiate as well. So that's quite important to know. Okay, so talking about switching, I'm just showing you a particularly poorly designed circuit here in this slide, which doesn't have any supply filter. And it's got the circuit has got a high degree of stray circuit inductance and capacitance, and therefore a low frequency and sharp peak. Using the faster the edge, the more energy is expanded in the ringing, which couples out in both common differential mode and causes a peak in your spectrum. Diagnosing this type of peak is quite simple. You can use an oscilloscope and look at this ringing on your scope, and then correlate the same ringing frequency with on your spectrum analyzer. So it's about fixing it is a little bit harder. So we need to just bear in mind that try to use snubbers if you can. Try to use minimize your high dB by dt and di by dt nodes, and on occasions a series ferrite on switching current path may be effective. In this example, I'm showing you how having a snubber circuit can affect and dampen the resonance of the parasitic components. So what I can recommend is that before you go to an EMI chamber, it's very good to go on the bench and check the switch node signals and the shape of them. Because what you will often see is the kind of ringing that you will actually see when you're doing your conducted emissions noise. Reduce slew rate can help, but there's so much you can do. You cannot just slow down the switching edges too much, because then your efficiency will go down. So there's a trade-off to find out what is best in your application. Okay, so this is where we started actually trying to fix the issue. So on the high voltage cable, if you remember, we were failing, and because in this application we didn't use any shielded cables, we had to focus on designing a multi-stage filter. So this is how the power PCB, I'll just put a picture of how the power PCB look like, and these two are the connectors of the output of the power PCB. And this is the filter that we designed. It's a multi-stage filter. We designed it and fitted it to the unit to see how it will improve the emissions. So we use different sections of this filter just to improve high frequency, low frequency, and also FM band. But at the end, when we try to fit this all the components into a PCB and fit it in the box, we couldn't fit the common mode choke here. So we just went ahead with the rest of the circuit, but no common mode choke was fitted. And this is how the PCB looked like. So basically we had the power PCB in the unit. It would connect directly to the filter, and the filter would connect directly to the HV connector. And then this was the outside world. So in this slide, I'm showing you the improved results on high voltage cable. This is the before picture without any filtering, any high voltage filter, and this is how much the filtering has improved. So you can see we got around more than 30 dB in below 10 megahertz, and then below 5 megahertz, and then in this region we also had improvements of 20 dB. And also the whole spectrum was quite improved compared to the result without any high voltage filter. On the low voltage line, which was the low voltage high current line, because we had really high current, there was only so much we could do. We couldn't add any inductors, big inductors or common mode chokes, because they would take a lot of space. So we could only apply capacitors between the low voltage rails and the vehicle chassis. So what we had in the circuit was a parallel MOSFET, and we had to make sure that we limit the impedance caused by the connection as well. So we added more capacitors for each half bridge, and also another thing that was very effective was adding low ESL and low ESR capacitance on both input and output. So it's these ones. It's worth noting that for decoupling capacitor, the size matters. We want to use the smallest possible size. MLCCs are very good for decoupling capacitors, but they do tend to resonate. That's why we've got in this circuit, we added a series resistor with each of these caps just to damp the resonance. And the inductance value also depends on how big the capacitor package is. So by having ceramic capacitor bank, you can cover a wide range of frequencies, which is what we've done here. You can see we use different values, 1 nanofarad, 100 nan, and other ones, and to cover the whole range that we were actually failing. So by making these change, you can see how much we made improvements in the low voltage line. It's around more than 20 dB improvement was seen. Actually, it's worth noting that in these graphs that I'm showing you, this is showing you the average results. So it has to be, the emission has to be below the red trace, which you can see here is failing there and failing a little bit here. So these capacitors made improvements, but they were not actually enough to fix all our issues. To help with fixing the emissions in the switching frequency region, we had to use some software switching techniques, which actually helped a lot in both our high voltage and low voltage cables. So you can see the before and after graph of both cables, low voltage and high voltage, and how much the emissions actually improved by using this switching technique in our software. Okay, so by this time we had almost fixed our high voltage and low voltage high current cable, but then it was time to look at our low voltage, low current issue. So this was mainly related to the control board. So we had a buck boost converter that was quite noisy. So we noticed that there was a break in our ground plane. So by fixing that and improving the layouts, we made huge improvements. And We identified layout parasitics, which caused noise, overshoot, ringing, and ground bounce. As you can see, I've highlighted here, there was a common choke already fitted, which was not suitable for the frequencies that we were failing, so we had to update that. We changed our inductor in this circuit with a shielded inductor, but bear in mind that even shielded inductors still emit a significant EMI. These capacitors to chassis from the rails were placed in not in a really good location, so we improved the location of that by improving our layout. And in the next slide, I'm also showing you how the layout actually was improved. So on here, we managed to, so we had to move the connector, we had to move the, as explained, move the common mode choke to the input right by the connector side, and we moved the power stage away from our connector and cables. We used a low ESR and ESL capacitor in both input and output side, and try to make the loop as small as possible. There was a break in our ground plane, as I explained, which we fixed that, so we had one good solid ground plane. And in the next slide, I can show you how it had actually improved our low voltage, low current line. So this is how it looked like before, from 150 kilohertz all the way to 30. And this one, this graph on the right hand side shows you the amount of improvement that we got from this cable. So this one shows you, these slides show you how we tackled the EMC test on the conducted emission line, the conducted emission test, but also for ST2 25, you have to pass radiated emission test as well. So the left-hand side pictures show you how we were failing the radiated emission test in both vertical and horizontal orientation of the biconical antenna, and then by fixing the conducted emission test and the noise, bringing the noise level down, we managed to pass the radiated emissions as well. So you can see that both average and quasi-peak levels are below the CISPR 25 test limit. That's all. Thank you very much. If you have any questions, please just put them in the chat. I'll start sharing. Sorry, Gani, I can't hear you.
That's better. Can you hear me
Yes,
now?
yes,
Okay,
I can hear you.
Yes, a fascinating talk. It's something we were looking into when I was at Warwick at WMG around simulating parasitics and the effects of switching. So yeah, so it's brought back some nice memories for me. Right, so yeah, I'm gonna ask if there's questions. Here we go, Martin. Did you do any simulation of these effects, Yegi?
No, we didn't do any simulation. We just simulated when we were designing the filters, we just did some simulations for the filters, but we didn't actually simulate the effects of, no, we didn't.
Mm-hmm. Do you think it would have helped or accelerated your work if you simulated, or?
I think it's quite difficult simulating parasitics and the emissions. It might have, because it was quite a strict deadline, so we just went all in and tried to fix and troubleshoot. So I don't think in this case it would have helped, but yeah.
Interesting, right. So there's a question here. Apologies, I'm going to get your names wrong. Blase?
Yeah.
What are the software switching techniques mentioned?
Sorry, can you say?
What are the software switching techniques mentioned? You mentioned about software switching techniques.
Yeah, I don't think I can disclose that. That's part of Lyra's. I'm sorry about that, but that's part of Lyra's novel.
Secret source. Yes.
So yeah, yes, but yeah.
Can you share about? So Jian's asking about switching frequency for your device under test.
It was 50 kilohertz.
50 kilohertz. Okay. Yeah. And the MOSFET device?
They were, you mean I think they were, I don't know what they were. I have to check. Probably Infineon. I'm not sure actually. I need to check.
Okay, yeah, very interesting stuff. So there, I guess, you know, this CISPR 25 standards,
Yes, it's better.
there's some very stringent radiated emission requirements. How do you ensure compliance against these requirements, especially across different frequency bands?
So it's quite important to think about your filtering. So the design incorporates filters specifically. You have to make sure that you tune your filtering specific to the challenging frequencies that you're having issues with. So that's one thing you need to think about. Electromagnetic shielding is quite important. So you can have your shielding of your entire converter. Having gaskets around your cable, the whole unit is quite important. And grid grounding is very important to prevent radiation. Looking at antenna effects and keep on testing, go back, iterate, test, and iterate. So,
yeah. Okay, yeah, interesting. And I guess, you know, we look at radiated emissions, but what about immunity to external EMC interference? Are the same things apply, or do you have to do something different?
That is a really good question. So it is very important, because if you have, for example, filters that are not robust to other interference coming from power lines, you need to basically redesign your filter. So you have to have that in mind. If you have input stage of your filters on the input stage of your converter, always make sure that you think about interference coming from the outside. Transient voltage suppressors, TVSs, are also good for protecting the converter from voltage spikes and surges. Component selection is very important. So just as I explained, use ceramic capacitors, low ESR inductors, and yeah, that's what I can think of.
Yeah, very, very interesting. Yeah, very good. Right, so I'm just going to open it up again to the audience for any final questions before we start to wrap up. Okay, seems like we've hit the end there. So, oh, there is something here actually. Yeah, Jan's just thrown one. Is ferrite better than snubber?
Snubber is more effective. Ferrite, I assume you're talking about snubbing the power switches, and I think snubbers are quite effective. Ferrites are sometimes effective, but I would definitely choose snubbers first. Select your snubbers, make sure that you tune them for the frequencies that you're struggling with, and then if you really have issues, then you can add ferrites, but always go with filtering first.
And then it's a question from Rod. Have you done work on traction inverters? This is an interesting one.
We have worked on inverters as well, yes. That's part of what we do at Lyra. We do work with inverters, converters, active front ends, everything. Yeah.
So, question about, again, selection of TVSs. How do you choose TVSs? Do you simulate, or
you can simulate? You can just based on practice and experience, you know what to use, and it depends on your voltages, what voltage surges you think you will expect to have on your connector side. So you have to have that all in mind. Look at the whole system and what it needs to be connected to as a whole system.
Similarly for the ferrites, yes, it's the same.
Ferrite is very important. You need to know what frequency you're trying to damp with your ferrite, and also choose a ferrite that will give you a highest impedance for that frequency range. So you need to choose the correct material, and then just pick them and try them.
Excellent. Okay, so let's call it a day there, because I think it's been an excellent talk. So good questions coming through as well. I'd like to thank Yegi a lot. Thank you, Yegi.
Thank you.
For I think fascinating. I think some of these topics are underrated, but they're really, really interesting. You know, having done some of this before, and challenging as well, because there's some really intricate issues that pop up, and you've got to be really ahead of the game on this. So thanks very much for sharing your experiences, and I really appreciate that.
Thank you very much.
So just to wrap up, I will just announce 2 or 3 things. We have our IoT SF Security, so our Security Foundation conference on the 23rd of October. So Chris has been kind enough to put the link in the chat. That's one of our showcase events, an excellent event if you're interested in hardware, software, enterprise level Internet of Things security. So I strongly recommend that as something you can share and circulate and attend if you can. We've also, our next tech talk is on the 18th of September, and it's being led by a company called 3SK Limited, based in Warwick University, near Warwick University in Warwick, who are experts in functional safety and systems design. Very strong automotive background, but they're also working in marine as well, again, and vertical liftoff, aircraft as well, technologies as well. So it's a very interesting talk. They're good friends and colleagues of ours, and that's on the 18th of September, and you can register for that on our ASIM website as well. You find the links there. And then we are scheduling a talk in October. At the moment, it was scheduled for the 23rd of October, but I think we're going to have to move that because that clashes with the IoTSF conference. So it might be a week or before or after, and that's a cybersecurity talk specifically around hardware cybersecurity. So with that, I'd like to thank the audience once again for joining us today and being so interactive in the presentation. And especially to Yegi, thank you very much again for joining us, and really hope we can work together in the future.
Yes, thank you.
Okay, wishing you all a very good afternoon and a nice day as well.